Hello and welcome back to Differential Equations, section 1.8, Acceleration and Velocity Models. We already seen the basic ones where we started with acceleration and we worked up all the way to position function, and we discovered the parabolic motion. So if we start with the fact that change in velocity over change in time is what we call acceleration, and we separate the variables, we integrate both sides, we have that the velocity is equal to at plus some constant c. Then we say that initial condition velocity at t equals to 0 is equal to some initial velocity v0, and we write that velocity at any time t is v0 plus at, which is the formula that you memorize in physics. And then from there we say that change in position, you can use, let's use, s is fine, dt is equal to our velocity function. Well, let me write velocity of t, which is velocity 0 plus at. We are going to again separate variables, leave s, which is the position on left hand side, move time to the other side. We have v0 plus at, everything dt. Again, we integrate both sides, and we get that the s of t is equal to v0 t plus at squared over 2 plus some s0. So position at time 0 is some initial position, which means that our function s of t is equal to 1/2 at squared plus v0t plus s0. Sorry, I wanted to say that this is some constant c, and then it becomes s0. So this is your parabolic motion. Now we know that acceleration for the object that you throw or drop is going to be gravity, g, acceleration of gravity. And then what you have, acceleration due to gravity. And then what you have is that it's also pointing downwards. So for parabolic motion, we will write that, actually use y now. Y of t for the height is negative 1/2 gt squared plus v0t plus y0, where y is the height, v0 is initial velocity, and then lowercase g is the acceleration of gravitation by constant. 9.81 meters per second, or 32.2 feet per second per second. So let's see what else. Now, just like in physics or earlier calculus, you have a problem to figure out what is the maximum height, at what time it occurs, how long the object was in the air, and all of that stuff that you earlier seen, you can do here, obviously. I mean, it's the same equations, the same concept. How would you find the maximum height that the object reaches for parabolic motion? What happens at the maximum height? Velocity is equal to 0, yeah. So for max height, set v of t equal to 0, and find time, t, at which it occurs, and then you can plug that t in the last equation, s of t, to find what that height actually is. So all of the stuff that you learned before obviously still stands across the whole thing. Now, there are also these concepts of resistance. While you, let's say, you know what would happen if you are to drop a feather and let's say a little stone, right, in the vacuum. What would happen? Due to acceleration of gravity, they would drop at the same rate. Very good. Now, do the same experiment here. Go to the 3rd or 4th floor and drop them. What happens? Air resistance, right? So feather is going to fall slow, and the rock is going to drop like a rock, right? So air resistance is good, right? Keeps airplanes and birds in the air. So we can work that out in our equations, and we'll see how that looks like. And also concept of terminal velocity is there from the same, because you just can't go past the certain, which is of course limit. You can't go past certain velocity because of the air resistance and whatever else. All right, so let's take a look at that derivation. Let's see. Well, had enough? I'll see you next week. So false, there it is, FR. So we're going to talk about resistance proportional to velocity. And we are going to talk about Fg, which is the force due to gravity. Gravity pulls. It's a weak force, but things still fall. So force due to gravity, and then we have Fr. Let me just write force due to gravity, and Fr, force due to air resistance in French. So force is going to be proportional to the velocity, and we'll put negative for the, let me just install the negative sign there. Yeah, okay, good. So force, their resistance is the constant times the velocity. Why is it negative? Because resistance, it's opposing, right? And now we can write also, we also know that the force is the mg, right, for the object that it's falling, which is the mass times the gravity. So the overall, and then again, that's negative because negative g, right, pulls down. So both of these have negative signs. Therefore, we have that the overall force is when we add these two. And we also have that force equals ma. Remember that one? That's a Newton's law, where we know that this a is change of velocity in time, right? So I will plug ma on this side, which is actually m dv dt. So we are going to have m dv dt is equal to negative kv minus mg. So this is the acceleration of the object, right? Mass of the object, acceleration of the object due to gravity, and the air resistance. That's how you should study all formulas that you see in physics or mathematics, because you think of the concepts that could go into the whole thing, right? So the object has to exist, so m has to be somewhere around, right, as a physical quantification of it. The initial acceleration, the acceleration due to gravity, and then, right, because gravity either helps or it makes it worse, right? The object that you throw up, gravity works against it. It decelerates it because it's g, right? Negative g goes down, right? So it decelerates. At the top, it stops and then changes direction. So when it stops here, that's that velocity equals to 0. And then acceleration of gravity pulls on it down. It pushes through the air down. So the whole thing over there now makes sense. And what we do is we divide through by m. M cannot be 0 because it's the mass of the object that we are observing. So divide by m. We get dv dt is equal to negative k over m v minus g. And as they say in the book, they define rho is k over m. So the final version of the differential equation is just going to be negative rho v minus g. What kind of equation is this? What kind of equation is this? Did anyone study? It's a linear first order. And how do we solve equations like this? Integrating factor. So I'm just going to write that on the side. I mean, you've seen the derivation. Now it's a matter of reading the problem, plugging in the numbers. But on the side, this is going to be dv dt plus rho v is equal to negative g. Oh, can it be worse letter than rho? Because integrating factor. When I learned differential equations, integrating factor was mu. And that didn't collide with anything. I mean, later on with some eigenvalues, but you don't use it for anything. Now I have to go, oh, actually rho, but this rho is for integrating factor and the other rho. They should really plan this a little bit better. I mean, that's why I have the books to match notation. Otherwise, I'll be using my values. But anyway, I'm just going to write it this way. Here be your P of t, your Q of t. Use integrating factor to solve the equation. Well, actually, wait. G is not a function, guys. G is not a function. Don't need this. G is a constant. What does that mean? It's separable, exactly. G is a constant. So, equation is, I've just seen that. So now we solve it. dv over negative rho v minus g is equal to dt. Integrate both sides. We get that on the left hand side, negative ln absolute value of negative rho v minus g is equal to dt plus some constant c. Distribute through the negative sign, so we get ln of absolute value is just going to make all of this positive. So rho v minus g is equal to negative, why do I have dt over here? It's just t plus c. Much better. Now again, I'm not changing sign of c because it really doesn't matter. E both sides. We have rho v minus g is equal to e to the negative t, and then there's some constant now, e to the c is k. Going to the next line. And we can solve for velocity here. K e to the negative t plus g, everything divided by rho. And that's the solution. So now what do I do with this? I take the limit as time goes to infinity, and that is going to be your terminal velocity. So limit of k e minus t plus g over rho as time goes to infinity, because you let the time go to infinity to see what's the fastest it can go. And that concept will be known as v tau, terminal velocity. Or terminal speed, right, if you just look at the magnitude of it. And now you just have variation on the topic. What happens if it's a square velocity? You just have v squared, you shuffle that through. Ah, you do this partial fraction decomposition at one point. That's good. That derivation should be a cool thing for you to enjoy at home. Variable gravitational acceleration. A lunar lander is free falling toward the moon, and the altitude of 53 kilometers above the lunar surface. Downward velocity is measured. Oh, okay. Technically, that's it. There's another application on page 95 for rocket propulsion. You want to work for SpaceX? You're the right age. And then, okay, that's it for the lecture. Let me just shut this off. We'll talk a little bit about some other stuff.